Welcome to Kip Hodges and his research group's Noble Gas Geochronology and Geochemistry Laboratory. My name is Hayden Miller and I am a postdoc working with Kip. Alex Pye, a graduate student in our group, and I will be giving a virtual tour of the lab today. The lab is located in the basement of ISTB4 and contains 5 mass spectrometers that allow us to determine the age of rocks through the measurement of parent radionuclides such as uranium and their resulting daughter decay products such as helium-4. We can also measure noble gas concentration gradients across a mineral domain. These gradients are imparted by thermally activated diffusion, most often the result of a geothermal gradient in the Earth's crust, and can be used to quantify the time temperature history of a rock, and therefore allow us to unravel geologically useful information like the history of erosion and tectonic uplift. The instrument you are now looking at is a magnetic sector noble gas mass spectrometer, a high-precision tool for the separation of isotopes by mass. For example, this instrument is able to separate helium-3 ions, an isotope of interest to us, from ions of hydrogen deuteride, a species with the same cardinal mass as helium-3, which we wish to avoid measuring. On the left is an ultra-high vacuum extraction line where we can purify and concentrate noble gases extracted from a mineral sample. These gases are ionized on a hot filament and accelerated through a magnetic field created here by the large blue magnet enveloping the flight tube. Ions of greater mass have their trajectory bent less sharply by the magnetic field than lighter mass ions, allowing for the physical separation of isotopes of interest. This instrument has a split flight tube design which permits the simultaneous detection of helium-4 ion beam on the far arm and a helium-3 ion beam on the arm closer to us.
This is our Raman microscope. It uses a visible light laser to produce a characteristic spectra of the mineral that you are analyzing. This spectra can then be used for identification purposes, or we can use it to detect how crystalline a sample is. For example, zircon becomes radiation damaged, and we can use this Raman to quantify the amount of radiation damage that it has had. This is the Alphachron. It is a quadrupole mass spectrometer, and we use this to measure helium isotopes. We use this in conjunction with the Icy PMS to do uranium, thorium, helium dating, and we have 2 different ways that we can do this. Firstly, we can do the conventional method where we load zircon or apatite or other helium-bearing minerals into niobium tubes, and then we degas them using an infrared laser. We then measure the helium isotopes using this machine. The other option is we can put the crystals, again helium-bearing crystals, into a mount, and we can do laser ablation work on them, and using an ultraviolet laser we can ablate small pits, and we measure the helium that comes out of that pit. This is the Icy PMS. It is a quadrupole mass spectrometer, and we use it to primarily measure the uranium, thorium, lead isotopes, as well as any other element that we might be interested in. We can use it in 2 different modes, the solution mode or the laser ablation mode. In solution mode, we are measuring the uranium and thorium isotopes in a dissolved crystal. This crystal we have already degassed for helium isotopes using the Alphachron or the SFT. The helium data, along with the uranium and thorium data, will give us a uranium and thorium and helium date. If we're using laser ablation, we are also able to get a uranium, thorium, helium date, provided that we have already drilled a helium pit using the laser ablation setting on the Alphachron or the SFT. We are also able to do uranium lead dating using this machine. We do this in situ with the laser ablation mode, and we drill a small pit and we measure the uranium, thorium, and lead content of the crystal. We are also able to do certain things such as rare earth elements at the same time. For example, if we are trying to look at the crystallization age of a granite, we can measure the uranium, thorium, lead date of a crystal, and we can also measure the rare earth elements at the same time, and that will tell us some of the conditions that that crystal crystallized in.
Here is a new Nobel S magnetic sector noble gas mass spectrometer. Our lab has two of these instruments, which we use for Argon Geochronology. Argon 40 is the product of radioactive decay of potassium 40. Due to the ubiquity of potassium in the Earth's crust, Argon Geochronology is an especially widely used method for determining the age of rocks. We utilize the Argon 40 Argon 39 method, where a sample undergoes neutron irradiation, triggering the transmutation of potassium 39 to Argon 39. This allows for an age to be calculated through a single measurement of argon isotopes. The Argon Geochronology undertaken in our lab can be broken into two primary categories: laser stepped heating, where argon is released as a mineral is progressively heated to hotter temperatures, and ultraviolet laser ablation microprobe analyses, which utilizes a 193 nanometer wavelength laser to ablate small volumes of sample in a polished thick section. This method is particularly useful for achieving high spatial resolution chronology in petrographically complicated samples. For example, in my own work, this method is utilized to study lunar breccias returned by the Apollo missions to understand the history of samples that have been bombarded by impactors for billions of years.